Hello friends and welcome. In this lecture, we are going to discuss one of the most important topics of communication system, that is pulse code modulation or simply PCM. PCM is the technique that connects the analog world with the digital world. So let's begin. First, let us understand why we need PCM at all. The signals around us, like our voice, music, and video, are all analog signals. An analog signal is a continuous in two senses, continuous in time and continuous in amplitude. Means it can take any value within a range. Now, analog signals are very sensitive to noise. Once noise gets added during transmission, it is almost impossible to remove it completely. While digital signals have only a few discrete values, so they can be regenerated cleanly and are far more immune to noise. So the idea is simple. Convert the analog signal into digital form, transmit that digital form, and then convert it back at the receiver. Pulse code modulation is the most basic and the most widely used technique to do this exactly. Now, let's see how does PCM convert an analog signal into a digital signal. It does this in three fundamental steps. Step 1 is sampling, the second step is quantization, and the third step is encoding. Basically, sampling makes the signal discrete in time, while quantization makes it discrete in amplitude and encoding represent it in binary form. Now, let us go through each of these steps one by one. This is the block diagram of a PCM transmitter. The analog message signal first passes through the low pass filter. This filter is also called the anti-aliasing filter, and it limits the signal to a maximum frequency, that is FM. After that, the signal goes to the sampler where it is sampled. The sampled output then enters the quantizer, which rounds each sample to a fixed level. Finally, the encoder converts every quantized sample into a binary code word. The output is a stream of bits, that is the PCM signal, ready for transmission. Therefore, the order of PCM transmitter is filter, sampler, quantizer, and then encoder. Let us start with the first step, that is sampling. In sampling, we take the value of the analog signal at regular time intervals. The time gap between the two samples is called the sampling interval, that is given by Ts, and the number of samples taken per second in the sampling frequency Fs. After sampling, the signal is no longer continuous in time. It exists only at the sampling instance. But notice carefully, the amplitude of each sample is still exactly the original value. So, sampling makes the signal discrete in time, but it is still continuous in amplitude. Now, how fast should we sample? The answer is given by the sampling theorem. It says the sampling frequency must be at least twice the maximum frequency of the message signal. That is, Fs must be greater than or equal to 2 Fm. The minimum rate is called the Nyquist rate. If we sample slower than this, the original signal cannot be recovered completely. After sampling, the second step is quantization. After sampling, each sample can still have any amplitude value, and there are infinitely many possibilities. A digital system cannot handle infinite values. So in quantization, we divide the entire amplitude range into a fixed number of levels. Let us call these numbers by capital L. Then every sample is rounded off to the nearest available level. The gap between the two adjacent levels is called the step size, and we denote it by delta. The step size equals to the total amplitude range divided by the number of levels L. After quantization, the signal can take only L fixed values, so it is now discrete in amplitude as well. After this step, the signal is fully discrete, discrete in time because of sampling and discrete in amplitude because of quantization. Now, here is a very important point about quantization. When we round a sample to the nearest level, the rounded value is usually not exactly equal to the original value. There is a small difference between the actual sample and the quantized sample. This difference is called quantization error or quantization noise. The maximum quantization error is half of the step size, that is plus minus delta by 2, and the average power of this quantization noise is given by delta square divided by 12. Quantization is the only step in PCM that causes loss of information. Sampling and encoding are reversible, but the quantization error can never be removed. Now, how can we reduce it? We can reduce it by increasing the number of levels given by L. More the levels means smaller step size, and a smaller step size means smaller error. But there is a trade-off. More level need more bits. So there is always a balance between accuracy and bit rate. The third and the final step is encoding. After quantization, we have n fixed levels. In encoding, each level is assigned a unique binary code word. The natural question is, how many bits do we need? If we have L levels, the number of bits per sample, that is n, equals to the log to the base 2 of L. For example, if there are 8 levels, then n equals to the log 2 of 8, which is 3. So each sample is represented by a 3-bit code. If we had 256 levels, we would need 8 bits per sample. After encoding, our analog signal has finally become a stream of binary ones and zeros, a true digital signal. Now let us calculate something very useful, that is the bit rate of the PCM signal. In 1 second we take fs samples and each sample is encoded into n bits. So the total number of bits per second, the bit rate RB, is simply n multiplied by fs. Let us take the standard telephone example. Human voice is limited to about 4 kHz. By Nyquist rate, the sampling frequency becomes 2 FM, that is 8 kHz. In telephone, we use 256 quantization levels. So, n is equal to 8 bits. Therefore, the bit rate is 8 bits multiplied by 8000 samples per second, which is given by 64,000 bits per second. That is 64 kbps. This 64 kbps is standard bit rate of a single digital telephone channel. So this simple formula directly gives us number used in real world communication systems. In order to recover the analog signal, we have PCM receiver, where we simply reverse the whole process. The incoming PCM bit stream is first passed through a regenerator, which cleans up the noisy pulses and restores sharp, clean ones. This regeneration ability is one of the biggest advantage of PCM. Next, the decoder converts the binary code word back into quantized sample values. Finally, a reconstruction low-pass filter smooths these samples and gives back the analog signal. One important thing is the recovered signal still contains the quantization error that was introduced at the transmitter. Apart from that small error, we get our original message signal back. Let us quickly summarize. PCM converts an analog signal into a digital signal in 3 steps. sampling, which makes it discrete in time, quantization, which makes it discrete in amplitude, and encoding, which converts it into binary. The three key formulas are step size, delta is equal to the range divided by L, bit per sample, n equals to log 2 of L, and bit rate RB equals to n times of Fs. PCM gives us excellent noise immunity, the ability to regenerate the signal, easy multiplexing, and secure communication. That is why PCM is the foundation of almost every modern digital communication system. Thank you.